For, well, centuries, the game in astronomy was pretty simple. You build a bigger telescope and you get to see farther. But we are in the middle of a totally new revolution, and this one isn't about giant pieces of glass and steel, it's about code, it's about algorithms. We're automating the very act of discovery itself. So let's dive into how AI is becoming our planet's brand new robotic astronomer.
So let me just start with a question that sounds simple, but is actually, profoundly difficult. How do you watch everything? I don't mean just pointing a telescope at a tiny patch of sky where you think something cool might happen. I mean all of it. The entire sky, all the time, looking for absolutely anything that moves or flashes or fades away. For a person? Impossible. But for a new generation of robotic surveys, hey, it's just another night at the office.
And this number is the result. The upcoming Vera C. Rubin Observatory is going to generate 10 million new cosmic alerts every single night. Think about that. Every alert is a little dot of light that wasn't there before. It could be an asteroid, could be a dying star. Maybe it's something nobody has ever seen before. It is a cosmic fire hose of data, and there is no army of astronomers on Earth that could ever hope to sort through it all.
And that brings us right to our first huge challenge, what we're calling the cosmic data tsunami. We are about to be absolutely flooded with more information about the changing sky than at any other point in human history. So the big question is, how in the world do we find those truly game-changing discoveries buried inside all of that noise?
I mean, just look at the sheer scale of this jump we're about to make. The current surveys, like the Zwicky Transient Facility, or ZTF, they already pump out up to 1 million alerts a night, which is, that's already mind-boggling. But the Rubin Observatory, that's a tenfold increase on top of that. It is a completely different league, and it basically makes all our old ways of finding things totally obsolete.
So how do these systems actually find anything new? Well, the main technique is actually kind of beautiful in its simplicity. It's called image differencing. You just take a brand new picture of the sky, and you digitally subtract an old reference picture of that exact same spot. Now, if nothing has changed, you're just left with blackness. But if a star has exploded, or an asteroid is moved through the frame, you're left with a little speck of light. And that right there, that's your alert.
Okay, but here's the catch. The vast majority of these alerts, they aren't real cosmic events at all. They're just digital noise. Artifacts from the camera. Maybe a cosmic ray zapped the sensor, or the images weren't perfectly aligned. We call them bogus alerts or false positives. And separating the millions of these from the handful of actual real discoveries, well, that is the first and maybe the most important job for a machine. So that brings us to the solution, the discovery pipeline. This is the incredible automated system that's been designed to tame that data tsunami we're talking about. You can think of it as the machine half of a new kind of partnership. It's the whole workflow that uses layers of software and AI to filter 10 million possibilities down to just a handful of confirmed discoveries, all before a human being even has to lay eyes on it.
And here's basically how it works. First, that image differencing trick creates all the raw alerts. Then, a machine learning model acts like a spam filter for the universe, throwing out over 99% of all the bogus stuff. Whatever's left gets passed on to these systems called alert brokers, which add more data and send them out. And then finally, even more specialized AI tools scan those real alerts, hunting for specific things, like a particular type of supernova an astronomer is looking for.
Now, this all sounds really great in theory, right? But does it actually work? Well, let's take a look at a real-world case study from the Zwicky Transient Facility's Bright Transient Survey. This is where we get to see the robot astronomer truly come to life. Just check out how fast this all happens. It's incredible. ZTF gets a new alert. Instantly, a bot called BTSBot flags it as a really good supernova candidate. That trigger then automatically tells a completely separate robotic telescope to stop what it's doing and take a detailed look. And then another AI model analyzes that new data and confirms it. Yep, this is a Type 1a supernova. The entire process is completely hands-off, all happening at machine speed. This quote from the research paper really says it all. Supernova 2023 TYK did not require any human action from its discovery to its spectroscopic classification. And that last part is so key. See, spectroscopic classification, that's how astronomers get a cosmic fingerprint of an object. They break its light down to figure out exactly what it's made of. And for the very first time, that entire chain of events, from a new blip of light to a full-blown scientific identification, happened with zero human intervention. It's a massive milestone. And get this This wasn't some lucky fluke or a one-time demo. Since that very first discovery, the system has gone on to automatically find and classify over 200 more supernovae just like it. This is the new normal for this kind of science. It is an operational discovery-making machine that is running right now.
But, of course, this amazing success, it creates a whole new kind of problem. You know what happens when you get really, really good at finding things? You create a new bottleneck somewhere else. The challenge is no longer just about finding stuff. It's about what you do next.
And this chart here, called the spectroscopic gap, shows the problem perfectly. That big bar on the left, that represents the massive number of new discoveries we're about to make. And that much, much smaller bar on the right, that's all the resources, the telescope time, we have to actually follow up and study them. As you can see, it's a huge mismatch. We're going to find at least 10 times more interesting objects than we can possibly study in detail. So the new question becomes, how do you decide which discoveries are actually worth our precious time? And this is exactly where that human-machine partnership becomes so crucial. Look, automation doesn't make astronomers obsolete. It just elevates their job. Their role shifts away from the manual labor of scanning through thousands of images to a much higher-level strategy. They're the ones building and improving these complex AI systems, deciding what science is the most important to prioritize and, this is the best part, using their human expertise to investigate the truly weird and novel things that the machines find for us.
You know, to build this future requires a whole new kind of team. It's not just astronomers in a room anymore. Success in this new era depends on this really deep collaboration between the astronomers who know the science, the machine learning experts who can build the actual models, and, let's not forget, the research software engineers who create the robust, complex infrastructure to make the whole thing work night after night.
So, with these incredibly powerful discovery engines coming online, what does the future of astronomy really look like? Let's talk about the scientific frontiers this automated paradigm is just about to unlock for us.
The ultimate goal here really is speed. For some of the most profound events in the universe, I'm talking about things like two neutron stars colliding and sending gravitational waves across space-time, those first few minutes and hours are everything. An automated system can react instantly, pointing telescopes all around the world to the right spot in the sky before the precious light from that cosmic collision even has time to fade away.
We are talking about opening entirely new windows on the universe. We'll be able to see the very first light from a star as it's ripping itself apart, not hours later when we get around to it. We'll finally have a reliable way to find the flash of light from a gravitational wave event, uniting two of our most powerful ways of studying the cosmos. And what's most exciting to me is that we will almost certainly discover completely new types of cosmic events, things we can't even imagine right now because they're too fast or too faint for our old methods to have ever caught. These systems can even create special data sets for citizen scientists, inviting everybody to join the hunt.
So let's just end with this thought. We are building machines to handle the monumental task of searching the sky. They're going to do the scanning, the filtering, the initial classification, all that grunt work. By freeing humans from that loop, we are empowering ourselves to ask much bigger questions. With the search automated, what profound cosmic mysteries will we, the human part of this incredible partnership, choose to solve next?